So I will basically report on a little side project which we did, but it turned out that even though this was supposed to be a little side project, there were some things that came out that we didn't understand at all, and some things we figured out, other things are still a mystery, and maybe you can figure it out, because we will stop, I think, with this little side project. So what I will do is revisit an old problem, namely the Fermi-Polaron problem, which was solved by Boris and Nikolai using the first code, diagrammatic Monte-Carlo code for fermions. And I will basically resolve the problem with a new determinant method, just to see how much better this method can do. So let me first I think most people are familiar with the problem, but let me just introduce it nonetheless. So we have an ideal Fermi gas in 3 dimensions, and to this ideal Fermi gas we add one impurity. So in red here we have the Fermi gas, and in blue the impurity. And then we add an we increase the attractive interaction between the impurity and the particles of the Fermi sea. And this interaction strength is characterized by this dimensionless quantity, where Kf is the Fermi momentum of the ideal gas, and A is the S-wave scattering length. And then what happens is that this impurity will be dressed with particle Hall excitations of the Fermi sea, and therefore it will renormalize its mass, its energy, and the quasi-particle residue will be different from 1. And then what Boris and Nikolai showed is that if this interaction strength is strong enough, then there is a transition to a state where this impurity will form a bound state with one particle of the Fermi sea, will form a dimer, and this dimer will also be dressed with particle Hall excitations. So that's why some people call this a dimeron.
Is it a transition or a crossover?
It's a transition, yes. So here you see that it's, this is, for example, the energy of the polaron, and this is the energy of this dimeron, and at some critical interaction strength, the two cross each other. Okay. So what is the model that we use to describe the system? So like the model is very similar to the model which Felix introduced for the resonant Fermi gas. So we just have a non-interacting dispersion for the ideal Fermi gas, and then we have a Hubbard type of interaction. So we actually have to put the particles first on the lattice, and B is the lattice spacing here, okay, and G0 the bare interaction strength. The bare interaction strength can be related to the S-wave scattering length through this relation from standard scattering theory. And now, if you want to take the zero range limit, meaning if you want to take this B, the lattice spacing going to 0, you need to do some type of regularization. Or actually, the system is regularized by putting it on the lattice. But we can take the zero range limit by summing these ladder diagrams, where this dot is the bare attractive interaction, and then this is the impurity propagator, and this is the single particle propagator of the ideal Fermi gas. So if you sum all of these ladders, you end up with this structure gamma naught, which is well defined in the zero range limit. So it will depend only on the scattering length A and no longer on the macroscopic details of the interaction. And then what we will do is build diagrams, for example, for the single particle propagator of the impurity, which are built from this gamma naught and the 3 single particle propagators. And in the original algorithm, we just do this in momentum and imaginary time representation and sum all the topologies and do the integration over internal variables through in a stochastic way through Monte-Carlo. So now what will be different is that we will work in position time representation. And all the diagrams have this particular structure where the impurity is always moving forward in time. And this is, for example, the structure of a diagram of order 4. And to calculate the weight of the contribution of the nth order Green's function, or the nth order contribution to the Green's function, we need to integrate out the internal variables, the internal space-times, and then its contribution will be just the weight of this backbone given the space-time points, and this backbone is just G0, gamma naught, G0, gamma naught, etc. And then this Sn contains all the contributions from all the possible ways you can connect these open ends. And as we have seen, this can be done in a single shot by just taking one determinant. So this Sn here is simply the determinant of a matrix A, and in the matrix elements are just the spin-up majority particle free propagators. Now, if you do that, there is one mistake that you make, because this gamma naught is the summation of all ladder diagrams, so ladders should be excluded from the calculation. But this is very simple here. What you can do is put particular zeros or put particular matrix elements to 0, namely if I is equal to j plus 1, then you will not have a propagator which goes from this endpoint of this gamma naught to the next gamma naught. And in doing that, you just immediately exclude the ladders. So we have seen in the talk of Felix that if you do this for the many-body problem, then if you have these zeros, you have the problem with spurious diagrams. Here is quite simple. You don't have any problem like that. If you want to calculate the self-energy, it can also be done quite simple compared to what we did before. We just have, again, this backbone structure. You need to integrate out the internal variables, which are just all these space-time points. You again have a backbone, which is just gamma naught, G naught, gamma naught, G naught, etc. And then you need to look at all possible connections of these open ends, but you need to exclude reducible diagrams. And this, as we have seen several times, it can be done with a recursive relation. So here you see it. But if you do this recursive relation for the Fermi-Polaron problem, it's actually much, much simpler due to the time ordering of this backbone. And if you analyze how much it costs to evaluate this at a given order n, you will see that it goes as n to the power 5. So it's not exponential, it's still polynomial. So then what we do in the Monte-Carlo code is just we have a configuration which is a set of space-time points. So Vn will be the set of space-time points at order n. X is the final space-time point. The weight of a configuration is just the contribution of the backbone times for G, this determinant. And then we just still reweight the different orders in order to sample all orders in a reasonable way. And we can also do some reweighting in time, which we typically do with this exponential. And then the algorithm is actually quite simple, and the code is super short. The updates which I implemented are just position shift, take one line, go from the old position difference to a new position difference. And how do we choose it? In order to propose a new position difference, we just take the short time, short distance behavior from the single particle and this gamma naught, which goes as 1 over delta tau to the 3/2 times this Gaussian. And for gamma naught, you have 1 over delta tau squared times this Gaussian. Then a time shift, just pick a line at random, change the time to a new time given its position difference. Another simple update is add. You have a backbone, and you go to one order higher by adding one gamma naught and one G naught at the very end. So you need to choose this space-time point x prime n plus 1 and a new final space-time x nu. And this, for these choices, we again use this short time, short distance behavior. And then we also have remove for the opposite update. So that's it. What do we get? Well, this is an example of such a calculation where here you see the end order contribution to the Green's function for momentum equal to 0 as a function of imaginary time for order 1, 2, 3, 4, 5. So you see this is at unitarity. you see that the signal seems to die out very rapidly. So in order to see this in a better way, let's plot Gn now at frequency 0.
Kris,
yes?
Did you take the absolute value here?
No.
Okay.
No. Okay, so this is what you get if you integrate over time. And now you can see that we actually, I went in this calculation up to order 30, but I didn't push it at all. I think you can easily go beyond that. And the series seems to, at first sight, seems to be nicely convergent. Okay, it converges very rapidly. But if we zoom in, you actually notice that there is a problem here. Okay, the oscillations are pretty small, but it doesn't converge at all. It's actually exponentially divergent. And this, as I will explain later, was actually quite a surprise to us. Here you see, again, a unitarity, the nth order contribution to the self-energy, same story. It seems to converge very rapidly. Seems to be, there seems to be nothing going on here, but if you zoom in, it's actually divergent. So let's try to understand this behavior better. And in order to do that, it makes more sense to look how the series behaves for a fixed total imaginary time. Okay, so let's go back to the curve as a function of time, but now at bigger orders. So here you see the Green's function, again at momentum equal to 0, as a function of imaginary time for orders 21 to 30. And this was actually quite surprising to us that it has such a behavior. So there is a peak, and then it's sign alternating, as we also saw in the previous plot. But it seems to be super regular, and in fact, it follows this behavior. It's a function of time, which is just rescaled with r to the power n, with r the radius of convergence. And for at unitarity, we have a particular value of r, which is close to 0.9. And we can check this behavior by just plotting, this is the same data as here, but we just take the absolute value and multiply with r to the power n, and indeed all these curves nicely fall on top of each other. So then we were quite puzzled because this is kind of a weird behavior. And we tried to understand why we can have, at least in principle, such an asymptotic behavior.
R is the function of k Fermi times A.
R is
a function of k Fermi times
yes,
A.
Yes. So this particular value is a value which is correct at unitarity, but it will be different. And then we started wondering, okay, are there particular classes of diagrams which might help us to understand why the series behaves like that? And then it was actually Felix who suggested, let's look at these guys here. And these diagrams had been considered before in the Fermi-Polaron problem. And how are they built? Well, we actually look at the so-called T3 diagrams, which are three-body diagrams. So these are the relevant diagrams if you consider three particles in vacuum. So you again have this backbone, and then you have two spin-up lines which jump one over the other, like two from one box to the other, like that. And then if you have such a structure for a three-body propagator, you can close it in two possible ways to get the self-energy or the Green's function. And if we look at only those two diagrams, we get something like this. This is the contribution of each of these diagrams. So in blue is one, in red the other one, as a function of the order. And indeed, we have the same behavior. It diverges exponentially. If you look at it in imaginary time, orders 21 to 30, it has exactly the same behavior. And if we take the absolute value and rescale with r to the power n, it nicely falls on top of each other. Moreover, the value of r is exactly the same. So somehow the asymptotic behavior of the Fermi-Polaron series comes from these two diagrams. Okay, but the function f is not the same. So it's not the end of the story because the function f, it's not the same if you take those two diagrams or if you take all the diagrams. And then the next question which we had was, okay, maybe this is a coincidence that R is the same, so let's look at different values of KFA. This is KFA minus 1, so it's on the polaron, deep in the polaron side. Same value of R for two diagrams and all diagrams. Unitarity, same value, okay? Same exponential increase. Then if we go close to the transition, this is like, there is a small discrepancy. But once we go to the BEC side, all of a sudden all the diagrams diverge actually more rapidly than those two guys. And we were not able to find which diagrams are actually responsible for that. We were guessing that maybe it's the 4-body or the 5-body which are closed in 4 or 24 ways, but I checked it and it's not that. Okay. So it's kind of maybe yeah, it would be fun to know where this comes from, but at this time we don't really know. So why does the series have this particular behavior? So let's try to answer that question, even also for those two diagrams. Well, initially we thought that the series would be convergent, and this was due to some old argument, which I think originally came from Boris, that if you have such a backbone in which all the propagators are ordered, then if we neglect the integration over position, and if we neglect the specifics of the propagators, if we say that they are just bounded by something, then this time-ordered integral over the internal times will immediately have a scaling, will give a scaling tau to the power 2n over 2n factorial. And since that there are roughly n factorial diagrams, in the end the contribution of all diagrams of order n will be tau to the power 2n over n factorial. So the series should be absolutely convergent. That's obviously not what we see numerically. So we try to improve this argument by including the integration over momenta, actually. We looked at we included the specifics, the specific form of the propagators and the integration over internal momenta. And now what happens if you actually put a momentum cutoff, a UV cutoff, then you can show that the nth order contribution will be bound in this way. So if you would consider the polaron series with UV cutoff, it will converge as 1 over square root of n factorial. So this tells us that somehow the fact that we don't have a convergent series but a divergent series, it comes from the ultraviolet behavior from the polaron problem. This is not true for all the diagrams. Actually, there are particular classes of diagrams which do converge in some factorial way. For example, if you take the lowest order self-energy and you just repeat this and create all reducible diagrams, then you will get, for example, contributions which die out as n factorial to the 3 halves. So now I will come back to those two guys, which already had the same behavior, this exponential increase as the behavior of the full series. And we actually have an argument why it's possible that these diagrams will have an exponential divergence. And for that, we will assume the following. We assume that each time here, each typical time difference of each line is small. And this makes sense because if n is the order, then 2n times delta tau should be roughly tau. So therefore, delta tau should be much smaller than the total time of the diagram. So now, since each of these propagators has a short time, we can use the vacuum part of G naught and gamma naught, which goes as 1 over tau to the 3 halves times this Gaussian and 1 over tau squared times this Gaussian. And now we compare this diagram at order n and at order n plus 1. So what happens is that if we take like the middle piece of this diagram, we need to add here this structure which is in dashed lines, which means that if we go from n to n plus 1, and if I take the ratio from n plus 1 and n, then we have an extra integral over two new variables, x tilde and x tilde prime. And then there are also three new propagators, namely this gamma naught, a g naught, and a g naught. Now, all the times are short, and therefore, if we integrate, it will be not advantageous, or it will be adding an order will be suppressed, because we have to integrate over time, which will give a vector delta tau, but we also need to integrate over position. But since we have this behavior here, the position will roughly go as square root of tau. So therefore, in 3 dimensions, we have this 3 halves. Same here, we have 1 plus 3 halves. But then on the other hand, if the time is short, then g and gamma, they will be large, okay? And actually, they go as, like I said before, delta tau to the 3 halves. For g and for gamma naught, it goes as delta tau squared. And these guys actually nicely cancel out each other. So you get in the end something of delta tau to the power 0. So you just get a constant. And therefore, you can keep on increasing the order, even for this time-ordered sequence. And you can get an exponential divergence. Okay, then we were also wondering whether it would be possible to get this full function f of tau. And here you see a plot of the nth order contribution to the self-energy as a function of tau. This is of these two diagrams, and this is of all diagrams. This is at order 30, and you see indeed that the two are not the same. And then we considered many different options, and the conclusion was actually that we could find many different diagrams which have the same scaling, the same exponential increase, but lead to a different function f of tau, and we were not able to tell you or to find a simple class which completely determines the asymptotic behavior, unfortunately. So here you see a couple of diagrams which actually also change this function f of tau, which amounts to addressing some of these lines at the end or in the middle. Okay, so then for the remaining time, I will just consider the resummation of the series. Since we have now 30 orders or more at our disposal, it should be absolutely no problem to resum this. And the way to do it, since we have a series with a finite radius of convergence, is to do a conformal mapping. And the conformal mapping which we will consider is this one here, which we, I think, saw in a few talks ago as well. So what happens is you always map z equal to 0 onto w equal to 0, and then the real positive axis is mapped onto the unit segment, and minus r is mapped onto minus 1. So then we still have some freedom here for the value of alpha. And this we will just change such that the resummation works very well. And this, by changing the value of alpha, what you will change is the region of the complex plane in Z, which is mapped into the unit disk. For example, if you take alpha equal to 2, what you will do is map the whole complex plane into the unit disk, and this cut here behind minus r is mapped on the unit disk. If you take alpha equal to 1 here, then you map a half plane into the unit disk. Okay. And in practice, what we did is take alpha equal to 1/2, because alpha equal to 2 and alpha equal to 1 didn't work very well. And for alpha 1/2, the region shrinks again. It's like a region like this of the complex plane, which is mapped into the unit disk. So here you see the result for the polaron energy. So it's a typical quasi-particle property which you can calculate from the self-energy by solving this equation. This is the polaron energy as a function of n, the order of expansion. And in red, I show results which were obtained by conventional diagrammatic Monte-Carlo. So we were able to go, or Boris and Nikolai were able to go to order 12, and it looked like at the time that it was convergent. But now with the determinant method, you can just really push it and go to, yeah, basically arbitrary order. And here you see the result up to order 30. Then you can do conformal mapping on top of that, and then you can get something like that, where you can get really an accuracy which is a bit. I told Martin Swierlein, who made this measurement, that he should try to get these digits, but he just started laughing. So yeah, so previously I think the accuracy was already very good. You had 3 digits, but now the error which I have is basically determined by the binning which I have. So it can be improved. And with that, I will conclude. So I've presented you the determined diagrammatic Monte-Carlo method for the Polaron. I think this is speaks for itself. You can just push it to very high orders and get an accuracy to, which is way beyond what was possible before. And then we see this large order behavior, which we don't fully understand, but at least we have some arguments why it's possible for the Polaron series to diverge exponentially. And then now what we are doing is doing finite temperature calculations for the Polaron, because recently the group of Martin Swierlein did measurements of the Polaron contact as a function of temperature, and there was some remarkable or some strange behavior that it first increases with temperature and then goes down again. So that's something we would like to understand. Something else which was mentioned yesterday is it would be nice to be able to do real-time calculations, but currently it's not clear at all how this is possible, and it's still here. Mainly also because of this problem, we don't know how to handle this. You always have like generalized Gaussians, which in principle do not converge. And you need to regularize it in a way that it can be handled in a practical way. And maybe, yeah, we would be nice to completely understand where this is coming from. Okay, thank you very much.
Questions? Jerry.
So your expansion is in the coupling, right? Between your...
Well, it's so it's a zero range. We take a zero range model. So we have you can start from the Hubbard model, but then this Hubbard model has an attractive bare coupling constant. But then we need to renormalize this bare coupling constant by doing the ladder summation. And the expansion that we do in the end is in gamma naught. It's already a renormalized object.
My question is, because you have a pole which is exactly on the real axis, negative real axis. Does it have a physical meaning, or?
So the fact that you mean in this figure here?
Yes, it is exactly on the real axis. Does it mean that this pole has a meaning in terms of, I don't know, repulsive interaction is attractive or something like that?
No, the only physical point here is z equal 1. Because z is a purely formal parameter.
Yes.
So like
true.
Kris said, we actually expand in powers of this object gamma 0, and then we can introduce z just by multiplying the order n by z to the power n. But z has no physical meaning except for z equal 1.
Still, the pole may still reveal. Still, the question is that the pole may still reveal some physics. That was the question.
I don't think so.
No, that was the question.
I mean, I think the answer is no.
Well, as long as someone can interpret the model with z being different from 1, they will be able, or you will be able to say what's the meaning of this pole, because it is just diagrammatic. There is, right? You can probably formulate the effective action, right?
Yes.
In which there will be z as a parameter, but it will be really the action rather than the Hamiltonian.
Yes.
Yeah, so that's what we do for the unitary
Yes.
as well, to do the resummation and so on. So indeed, formally you can extend the model to complex arbitrary z, but it's not physical anymore. But yeah, it can still be interesting indeed to think about it.
More questions? Yes.
So is the power counting argument basically shows the self-energy basically is marginal? Is that because it's is that what you are saying about the power counting argument?
No, it's what the only thing which I try to argue is that if you compare the two orders here,
yes,
that you need to.
It's constant. Right?
Yes.
So
yes.
basically that's basically it's a marginal operator, basically in the RG language.
Okay.
So and basically you can also remove this oscillation by use a renormalized diagram where self-energy is a result. And there's a constant piece of self-energy is result. You can also remove this oscillation, I think.
Possibly, yeah.
But we don't know how, because as Kris said, it's not just these diagrams.
Yes,
there are many
more
which have similar behavior.
It only says the constant piece of the self-energy is marginal. Then you resum all constant piece of your self-energy, and not matter which diagram comes from. Right? Just the constant piece.
Okay, you will have to explain this.
Okay.
Other questions? Doris?
Could you go to regimes that were very difficult before, like very heavy impurity mass?
So this is definitely also something which is worth trying, because with the old method it was very difficult to go to mass ratios which were different. Here I think it should be possible given these results, but we didn't try. That's definitely on the list. I didn't put it on the list, but it's on the list.
Okay.
Also in 2D it was much more difficult. The calculations in 2D were more difficult than in 3D. So I think now
your T matrix doesn't even properly exist.
Hmm?
I mean, your T matrix becomes a distribution in 2D, so it's going to be even worse than here. Your gamma is a problem in 2D. Right?
Okay, I will have to think about
one
it.
over log, which so this is why we did quasi 2D to have a.
Yes.
So I think in 2D it could be a lot worse. I don't know.
I don't know. I'm not sure. Okay.
More questions? Okay, let's thank